Hello everyone, welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. Welcome, good to see you again, even though I'm not seeing you. This is about galvanic cell potentials, so we're going to get into some of the quantitative stuff related to galvanic cells and actually calculating the voltage that certain cells are capable of producing. You need a couple of things for this. You're going to need table 24 in your data booklet. It looks like this. Also, this presentation goes with a note sheet, so rather than writing down all these word for word, there's a note sheet in your data booklet. I think it's titled, galvanic cell potentials. I think it starts talking about the redox and the electron battle right away. You guys are smart. I think you can figure it out. But make sure you have those two things before we proceed. So, we're going to get redox, oxidation, reduction reactions as a battle of electrons. Some elements or ions are great at taking electrons, others prefer to give them up. Now, I hate to use that word prefer because atoms don't prefer anything, but there is a certain force. Electrons are going to tend to go to a place where they're at a lower energy state, so that means that some species will tend to give up electrons, and others will tend to take it, because electrons will be in a lower energy state when that other thing takes the electron. So we can kind of think of it as a mountain, and think of the ones that are at the top of the mountain are the ones that would easily give up electrons, and then the ones at the bottom are the ones that are going to be taking electrons. So electrons are going to flow downhill spontaneously. They're not going to flow uphill on their own. That's sort of analogous to what happens in an electrolytic cell, which we're going to get into later. But these electrons are flowing downhill. And basically, the farther the distance between these two species on this little magical mountain, the greater the force by which those electrons are going to want to sort of move between those two things. That's called the electromotive force. So to have any hope of understanding this stuff, we do need to understand some basics of terminology. So some things you probably heard before but maybe didn't know exactly what they were. Voltage is a measurement of electric potential, and amps measure current. So as an analogy, you know what, I'll get into this analogy in a second. The definition of a volt means that 1 joule of work can be done per coulomb of charge. Coulomb is the amount of charge in 6.24 times 10 to the 18th electrons. And then an amp suggests 1 coulomb per second. So basically the voltage is again, it has to do with the electric potential difference between two things. And then the amp is more to do with the quantity of electrons that are moving through. So this is in the Grand Canyon. This is called Lava Falls. It's kind of hard to tell from this picture, but it is considered a waterfall. Not a super steep one by any means, but a tremendous amount of water flows through there. And then this is some, I don't know, random falls in Hawaii. Seems to be, although we don't have any scaling here, it seems to be a much taller waterfall, but much less water flowing over it. So this one here would be more like a high voltage, low amperage type situation, where this is low voltage because it's not very tall, but high amperage because there's a lot of water going through it. When it comes to the deadliness of electricity, a lot of times it's more to do with the amperage rather than the voltage. People talk about voltage, oh, high volts, it's dangerous. Static electricity, like a static shock, for instance, is an example of a very high voltage type discharge, but very low amperage. The amps tend to be more dangerous than high voltage per se. So actually, many years ago, I was fortunate to actually go through the entire Grand Canyon, and I rode on a raft. It was a 9-day trip. It was awesome, one of the best things I've ever done in my life. But this is actually me. I think that might be me right there. We were going through Lava Falls. This picture cannot do justice to just how gnarly and amazing Lava Falls is. So it was pretty cool. It was pretty fun. And yeah, this is us after we made it through. That's me right there again. So yeah, that was a lot of fun. And if you ever get the chance, I would recommend that you at least go to the Grand Canyon at the top. But if you could go through it like I did, that's even better, I think. So thinking back to the stuff we've been talking about galvanic cells. So if you hook up two half cells to make a galvanic cell, and there's electrons flowing through them, it is the electromotive force that's driving them. Now we can quantify this force. Again, that's kind of what we're talking about here. So the electromotive force between two half cells is sort of like the theoretical maximum energy difference between the two, and we can use volts to talk about that. Now, when you actually hook up a cell and it starts running, you're never going to quite get that theoretical maximum because You're going to lose some of the energy to resistance as electrons flow through the wires and all that kind of thing. So the voltage of a cell that's actually running is called the cell potential. Both EMF and the cell potential can be measured in volts. It's just the actual cell potential is going to be a little bit less than the EMF. So, what would be nice to know is the electric potential of any particular half cell. Because if I take two half cells and I put them together, I would maybe want to know what kind of voltage can this galvanic cell produce before I build it. The problem with that is you can't assign voltage to a half cell because voltage is only a relative thing. It's what is the difference in electric potential between these two species, and it's only relative. It's only a relative situation, so therefore I couldn't assign a voltage to a half reaction or to a half cell. But scientists figured out a way around this problem. Is they made this electrode that they called the standard hydrogen electrode, and they based everything off of that. You do need to know what the standard hydrogen electrode is, like how it's made. So basically, I'll show you a picture of it. You've got glass, you've got hydrogen gas being pumped in through here at a pressure of 1 atmosphere. You've got hydrochloric acid solution with a mole per cubic decimeter, a concentration of 1. So the HCl concentration is 1, and then a platinum electrode. And again, I would jot down maybe a picture of that, or these key details here that I have here. It also needs to be at 298 Kelvin or 25 Celsius. So they arbitrarily assign this thing a voltage of 0, and then they connect other half cells to the hydrogen, and then they can actually assign a reduction potential or an oxidation potential to any particular half cell. And so basically this is how the whole thing is scaled. The table of electric potentials I'm going to show you in a second. It's all scaled to the fact that we're going to call the standard hydrogen electron 0, and everything else is in comparison and relative to that. And again, you do need to know the specific details. You'll be asked specific details about the standard hydrogen electrode, both on IB exams and on this test. So it's one of those things you want to commit to memory. So, after they figured out, okay, let's make the standard hydrogen electrode, let's assign every half reaction voltages based upon that. And then let's make a table. And by convention, there are tables of reduction potentials. So basically, they take all of these half reactions, they write them in the reduction form. And one thing to keep in mind about all this stuff is the more positive the value is when you're talking about electric potential, the more spontaneous or the more likely it is to happen. So the more likely something is to be reduced, for example, the more positive of a reduction potential it's going to have. Now, of course, since it's redox, you can't just have a reduction, you have to have oxidation as well. So if you want to know the oxidation potential of any particular thing, you just flip the reduction potential and then also flip the sign. And so although the table is a table of reduction potentials, we can use it to find oxidation potentials as well. And it's really, I know this kind of probably sounds complicated, it's not that hard really to find these as long as you keep a few key things in mind. So what we want to do, let's say we're looking at a galvanic cell, maybe a classic copper zinc half cell or whatever. All we need to do is add up the reduction potential of the reduction reaction and the oxidation potential of the oxidation reaction, and just add those two voltages up, and that will tell us the voltage of the cell, the electromotive force. And then again, the cell potential when we actually run it is probably going to be a little less than that due to some resistance. And if a galvanic cell is a spontaneous, so by definition, galvanic cells revolve around spontaneous reactions. Spontaneous reactions are going to have positive electric potential differences. So potentials on the table 24, just like with the standard hydrogen electrode, they assume you're running at 25 Celsius. Any concentration of any ions that are present are 1, and any gases that have to be present are at a pressure of 1 atmosphere. So that would be, well, we'll talk more about some of the gas electrodes and some of these weirder electrodes. But yeah, these are the standard electric potentials. The little e theta usually thing is up there. Oh yes, and then we have I don't know. I just thought it was time for a classic GIF, or is it GIF? Shaq, cat, love it. Let's see here. No, I don't think you got that. Yeah. Anywho. This is the table. This is the table of reduction potentials. That's in table 24. So we can see at the top is an Li plus gaining an electron. That is a very negative reduction potential. That means that's not very likely to happen. All the way down here to fluorine, the most electronegative element, so neutral fluorine in the gas state, gaining an electron. I think my head is maybe over it. 2.87 is the voltage there. Oh, hey, I can move myself around. Hello! I just realized that. Hi! And then I can like look down. Anyway, maybe I'll go up here just for fun. All right. So, how do we go about calculating cell potentials? Like I said, it's pretty easy as long as you keep a couple of key things in mind. You're going to split a reaction that you're looking at, the overall reaction for the galvanic cell, into oxidation reductions and determine the electric potential each. So you can find the reduction part of the half. You can find the reduction half reaction right on the sheet, hopefully. To find the oxidation half reaction, you'll need to find a reduction reaction that is exactly its opposite. Be very careful. Make sure that all the charges and everything are the same, and all that makes a huge difference. So make sure the thing that you're seeing is exactly the opposite. Same thing for the reduction reaction. Make sure that that's exactly correct. Now, when you balance this part is tricky, and this is the part where people will make a mistake. When you balance the reaction by multiplying each half reaction by a coefficient or whatever to balance, and I'll show you an example in a second, that does not change the electric potential. So whatever you're doing, if you're using this table and you think there's some reason that you should multiply this by something, you shouldn't, and I'll explain why in a second. And then you just add them. And if it's a galvanic cell that's actually functioning, when you do add the potentials of the two half reactions, it must be positive. If you don't get a positive answer, either it's not an actual functioning galvanic cell, the electrons are going to be going the opposite way that you think they are, or you've done something wrong, or whatever. If it is an actual functioning voltaic cell with a spontaneous reaction, it should have a positive total electric potential. So, let's take a look at this one. Let's say we've set up made a galvanic cell and it operates on this reaction. So it's a magnesium and aluminum electrodes, and this is the overall reaction. So what kind of voltage can this cell produce? Let's calculate it. So if we pop back here, we're going to split this into the half reactions. We're going to figure out the potential of each one of those, and then we're going to simply add that together. So what I'm seeing here, this is already a net ionic equation. And plus 2E minus. So we've got the magnesium going to Mg2 plus 2E minus, and then we've got the Al3 plus 3E minus going to aluminum. So we've got the magnesium being oxidized and the Al3 plus ions being reduced. So I've got my two half reactions here. These half reactions are not balanced for charge. I got 2 electrons over there and 3 electrons over there. As I think we've probably talked about, one way to balance half reactions is just to go like this. I would have to multiply that top one by 3, and have to multiply this bottom one by 2. This is fine to balance it. In fact, I'm not going to multiply those all out or anything. There's my 2 half reactions. And then now we need to find them on the table. Okay, so the aluminum, the bottom one, that's my reduction. So hopefully I can find that directly on the table. I've got to make sure that it's exactly the same as the one I've written. So Al plus 3 gaining 3 electrons going to aluminum. Yep, that's it. Negative 1.66. So this is negative 1.66 volts. And again, I'm not going to multiply it by 2 because of that right there. Now I've got to find the magnesium one. Now this is an oxidation. This table only has reductions on it. So basically what I need to find is something that's exactly the opposite of what I have on that page. And it's this one right here. If I think of this completely reversed, we've got a magnesium going to Mg2 plus and 2 electrons, which is what I have there on the top. So this reaction as a reduction has a potential of negative 2.37, but as an oxidation, I flip that. So positive 2.37 volts. And then I just add them, and comes out to like 0.71, I believe. I think I have it all worked out here. Yeah, so we have our half reactions there. We have it balanced. Just add those together. So that cell, a galvanic cell that is made using that chemical reaction, would have a potential of 0.71 volts. And so really pretty simple, especially in these either galvanic cells, as long as you remember that this doesn't actually affect the voltage. And, possibly at first glance that can seem a little confusing, but I promise, again, especially with these more basic galvanic cells, you guys will crush this. This is not that bad at all. We'll do more examples in class. Oh, and I think that, yeah, there was a question there about what was the anode and what was the cathode. Remember, oxidation at the anode, reduction at the cathode. So our anode is going to be there's going to be magnesium at the anode and aluminum at the cathode. So the anode is going to be magnesium and Mg2 plus ions. The cathode is going to be aluminum and Al3 plus ions. So it's a fair question to ask. Well, it seems like you should multiply those volts. That seems like that's what you should do. I'm multiplying the whole reaction by 3. Shouldn't I multiply these volts by 3 as well? No. Voltage like density is an intensive property. We've talked about intensive properties. Intensive properties are those that do not, the size of the thing you're dealing with doesn't matter, or the amount. So density is mass over volume, of course, as we all know. So if you had a little gold nugget, that's a little gold nugget, and you had a gigantic gold nugget, they both have the same density because although the mass is larger in the larger gold nugget, the volume is larger as well, and the density ends up being the same. Well, volt is a similar type of thing. A volt is a joule. It basically means a joule of work can be done per coulomb. So it's a ratio, like density. Density is a ratio of mass to volume. Voltage is a ratio as well. So if you double the number of electrons, or triple them, or whatever, if you're multiplying by some coefficient, that does change the joules, but it changes the coulombs at the same time. So if it triples the joules, it also triples the coulombs. The ratio remains the same. So that's why when we're looking at electric potentials, that's why we don't multiply. In that case, we just use the electric potential as it says in the sheet. So another thing I want to talk about here quickly is there's a way to convert between Gibbs free energy and cell potentials. And there's a little equation, decently easy to use. You'll find it in your data booklet. So Gibbs free energy must be negative in a spontaneous process. That's something we talked about in the energetics unit. This is the little equation, again, it's in your data booklet. Gibbs free energy, this is moles of electrons transferred. This is something called the Faraday constant, which is the charge of a mole of electrons. So it's 9.65 times 10 to the, there are 9.65 times 10 to the fourth coulombs in a mole of electrons. And then the E, this is the cell potential, the standard cell potential that we calculate. So if we this is a constant, so we can just figure out this N and this E. We can make this calculation. So finding the delta G for this reaction that we already looked at, do we expect a positive or negative answer for this? We expect a negative answer because we already figured out that as a positive voltage, that means it's a spontaneous reaction, and therefore its delta G should be negative. Alright, so let's just solve for this real quick using this reaction that we already did already. Now, thinking back to the one we calculated here, so N, the moles of electrons transferred, is going to be 6. Because if 2 times 3 is 6, 3 times 2 is 6, there's actually 6 electrons being transferred here. So delta G equals negative sign, 6 electrons being transferred, 6 moles of electrons, so that's 6 moles, times the Faraday constant, which is 9.65 times 10 to the fourth coulombs per mole, and then we calculated before previously, this is 0.71 volts, but just for the purposes of units, a volt is a joule per coulomb, and the coulombs are going to cancel here, and the moles are going to cancel here. We're going to get an answer in joules, and so basically it's 6 times 9.65 times 10 to the negative fourth times 0.71. We get negative 411,090. Again, that's joules. Let's just change it to kilojoules to make our sig figs. So again, makes sense. We should have a negative voltage here. This is a spontaneous reaction, so positive voltages go with negative delta G gives for energy values. All right, guys, I think that's it for now. We'll talk about this more in class. Thank you so much for watching, and enjoy the rest of your day.